In this video, we're going to be talking about graphing polar equations. In the last video, we graphed individual points in polar coordinates, and we talked about converting between Cartesian and polar coordinates. And the focus here is just going to be on entire graphs of polar functions. So, let me get started on this. So, last time again, we already know, so we saw how to do this, we already know how to graph individual points. I'll need that table in a minute, sorry. So we already know how to do individual points. We did that last time. What about entire equations? Well, we can do that too. And the easiest way to do it is just by examples. So that's what we're going to do. Let me start off with a relatively straightforward one. Here's my equation in polar coordinates. It's just going to be r equals a number, in this case 8. What we're saying in this equation is that, again, we have two variables to work with, r and theta. We're giving no restrictions on theta. Theta can be anything, but r is fixed at a value of 8. So if I were to draw this, get my axes, here's my x and y coordinates. The idea is that theta is going to spell out an angle measured from the positive x-axis as we go around this thing, and r is going to tell us how far from the origin to go. And in this case, we're going to start right here. At theta equals 0, I'm going to say this value right here is 8. And as theta increases, because again there are no restrictions on theta, theta can be anything, as theta increases, what is happening to r? So when I go out in this direction, what is the value of r? Well, it is still a distance of 8. And when I go in this direction, what is the value of r? Well, it is still a distance of 8. And all that's happening is that we're going to be drawing basically a big circle. And that's exactly what this is. So we work our way around and we draw a big circle in this, going in this direction. So this is what the equation r equals 8 looks like. You can think of it in a sense of as us plotting a bunch of points along the way. One way that we'll see that we can do this is setting up a table with r values and theta values. And we're saying, so when theta was 0, what was r? Well, it was 8. And when theta was maybe pi over 4, for example, what was r? Well, it was still 8, because r is equal to 8. It's always 8. And we could change the values of theta, starting here, going over here, going over here, and r stays 8 the whole time. Well, there we go. And so this would continue on indefinitely. So this is going to be one approach that we'll have, basically doing a little table and using that table to plot points and then playing connect the dots the same way that we would doing this for a Cartesian graph, for example. But this is it. This is what the graph looks like. We'll have a better way to do this where instead of drawing a table, what I will actually do is draw something in the r theta coordinates. We'll do that in just a minute after we do a couple simple examples. So let's start with these. We've got r equals a constant. Let's have our next example be, what do we get if instead of letting r be a constant, we let theta be a constant? So let's let theta just be pi over 3. So now r can take on any value. There are no restrictions on what r can be, and it's theta that is specified. So again, I'll draw my axes here. We've got my x and my y. Give myself more room. And basically we're saying that angle right there, that we should recognize as being about pi over 3. And r can be anything. So r could be 0, r could be maybe, if this is a distance of 1, r could be 2, r could be any value in between. And so what we get is just a solid line. There's all the positive values of r, but r can also be negative. And so we could go this direction and get all the negative values of r. And we wind up with just a straight line. So when theta is a constant and r is the thing that has no restrictions, we're just going to every distance from the origin, every possible value of r along, or that maintains this angle of pi over 3. And that includes positive r values, which would put us up here in the first quadrant in this case, and negative r values, which would put us down in the third quadrant for this particular example. So that's what the two graphs look like. There's r equals a constant, there's theta equals a constant. One is a circle, one is a straight line. So let's look at some increasingly complicated examples. Here's a really common one that we'll see, so I want to make sure we're comfortable with this. R equals cosine of theta. Similarly, r equals sine of theta. Whenever we just have r equals just one of those two basic trig functions of theta, what does the graph of this look like? So again, we can do this with a table. Let me set up my axes. Here's where we're going to draw our graph in just a minute. There's the x and the y. And here is going to be the table of values, where I will give combinations of r and theta. And so let's pick some easy values of theta. Let's do like 0, pi over, let's do all the ones we know from the unit circle. Sorry for that jump. Here we go. Pi over 6, pi over 4, pi over 3, pi over 2, and we can continue on if necessary beyond that. So if I take the values of theta in this table and plug them into our equation, what value of r do they spit out? So when I plug in theta equals 0, so the cosine of 0. What is the cosine of 0? The cosine of 0 is, again, just memorized from our unit circle, cosine of 0 is 1. And then if we go to plug in pi over 6, what is cosine of pi over 6? Well, that number is root 3 over 2. And what about when I plug in pi over 4? Well, that is that is root 2 over 2. And pi over 3, we get a half. And by the time we get up to pi over 2, we're all the way down to 0. So I'm going to approximate these values just so we can get some decimal approximations to figure out how far to draw this. Root 3 over 2, root 3 is about 1.7-ish. I don't know the decimals after that, but in that ballpark. So if we divide that by 2, that puts us at about, oh, come on. That puts us at about 0.85-ish, somewhere in that ballpark. Root 2 over 2, root 2 is about 1.4. If I divide that by 2, we should get about 0.7-ish, somewhere in that ballpark. And obviously 1/2, 0.5. That one's pretty easy. And so I want to think about plotting these points. The first one, when theta equals 0, means I'm pointing straight along the x-axis, and we're going out a distance of 1. So there's my first point. And then when I get to an angle of pi over 6, which we're going to say is about right there, let me draw all the angles in that we're going to need. There's going to be pi over 4, there's going to be pi over 3. So here's all the angles that we're going to check. At pi over 6, the distance was about 0.85. So hypothetically, if we maintained a distance of 1, that would look something like this. That would also be 1. So 0.85, if this is a distance of 1 right here along this direction, 0.85 would be, I don't know, maybe here-ish. So that's where I'll draw my dot, right there-ish. And similarly, here's the one where we're supposed to draw, so this is pi over 4, we're supposed to draw root 2 over 2, which is about 0.7. I'll say 0.7 is maybe there-ish. And by the time we get to pi over 3, we're supposed to be all the way down to a half, which I'll say is about there-ish. And by the time we get all the way up to pi over 2, the radius is down to 0. And what we get is a shape that goes through those points. And if we continued to the angles over here in the second quadrant, we would get this same list of numbers. If I did, for example, if I did 2 pi over 3, so the angle over here, we would continue to get a lot of these same numbers, but in the reverse order. What we'd wind up actually getting is tracing out a bottom half that looked exactly the same as the top half. And in this case, the shape that we get out of all of this, erase that right there, the shape that we get out of this is an off-centered circle. So going back up to the other twos, let me just write down real quickly what we got. This one was obviously what I'm going to call a centered circle, meaning it's centered at the origin. This one was just a line through the origin. And now we've got an off-centered circle. The table that we used can be a little bit clunky, so in my opinion, a better way to think about this is to actually, instead of using a table, actually do a graph of r equals cosine theta in our theta space. So let me show you what I mean by that. So an alternative approach to this one. So a better approach, in my opinion. So the graph that where we got the circle right here is in the xy coordinate system. We're graphing a polar function in the Cartesian coordinate system. I want to graph this polar function in the polar coordinate system, meaning I want my two axes to be theta and r. And I want to think about what this graph is. It's saying r equals cosine theta. So let me just copy that down here. R equals cosine of theta. Well, essentially what we're doing is kind of letting these two pieces play the role that might normally be thought of as like y equals cosine of x, where we call this x and this y. Put those in parentheses down there. And we know what the graph of y equals cosine of x looks like. That's easy. It goes up to a height of 1, down to a height of -1. It stays between these two lines. And it completes a full period after a distance of 2 pi. So if that's 2 pi, then we'll say that that's about pi. Here's the pi halves and 3 pi halves. And we're going basically up through this point, down through this point, up through this point. Right, going that way, doing something similar. Not even going to bother to worry about the details on this side, but same thing. It's symmetric like this. This part of the graph right here matches what we just wrote in the table. We can think of starting at a value of theta of 0, so that would be right here, and figuring out what is the corresponding r. So here is theta equals 0 and r equals 1. That's exactly what gave us this first point. And as we go through this, we made it all the way up to this point. So if I went to pi over 6, that's going to be right here-ish, and the height was 0.85-ish. And we went to pi over 4, that's right here, and the height was 0.7-ish. And we went to pi over 3, which is over here-ish, and the height is about a half. And then we made it to pi over 2, where the height was 0. This smooth curve represents all of these numbers that we came up with over here. We're translating basically from the table. And this is going to be, excuse me, in a lot of ways, this is going to be an easier way to track the values that we want here. All I really need to know is that I started off when theta was 0. Again, theta was 0, r was 1. That puts me at, on this graph, theta equals 0, here's r equals 1. And what is happening to r over this region? It's decreasing. And it's decreasing all the way down to 0. Here's where r is equal to 0. By the time I get to theta pointing straight up over here, that's the equivalent of this point right here, pi over 2. And then it continues as I start to go into these thetas that are in the second quadrant. That is this part of the graph. So if you want to think about it, this region here, ooh, here's our quadrant 1 region. Jeez Louise. Here's our quadrant 1 region, here's our quadrant 2 region, as we kind of split between these things. I need to actually undo that. What I really want to do is, let's see if I can erase this. There we go. On our unit circle, let me erase this one as well. I'll write them in a nice, neater place. Okay. This first region is quadrant 1. This second region is quadrant 2, quadrant 3, quadrant 4, and then we're all the way back to 2 pi. We've completed our full rotation around the unit circle. So this region in quadrant 1, we started at 1 for our value of r, and we went down to 0. Because this is what we're thinking of graphing. R was 1 down to 0 as we went from this direction, theta equals 0, to this direction, theta equals pi over 2. Now as I go from pi over 2 to pi, our second quadrant region, that's this region, that entire region, what are the values of r? Well, it's exactly the same shape that we did here, but now all the values of r are negative. It's like the negative mirror image, which is why I know that I will get the negative mirror image and get this same drawing. And in fact, I've completed this circle by the time that I get to this point, basically, when I'm aiming in this direction. By the time on this graph we get to right here, because I'm pointing in the direction of theta equals pi, meaning I'm pointing in this direction on the negative x-axis. But what is my radius down here? My radius is -1. So I'm pointing this direction, but the -1 means we turn around and we wind up back at the point that we started at right here. So that's kind of the idea. This is how I like to draw my graphs. I like to draw one in our theta coordinates. This is what will look like a traditional graph that we learned how to do back previously in chapter 3, I think, when we did graphs of trig functions. Maybe it was 4. And we'll just translate this point by point into the polar picture. So we can try this again on a couple of problems, and then I'll show you how to use Desmos to make this even easier. And I would highly encourage you to use Desmos for some of these problems if you get stuck. So let me try, I don't want to do all of these examples. Let me try this one. r equals something relatively simple, 1 plus the sine of theta. So I'm going to actually start with my r theta graph. So I'm going to start with the one that we did second last time. So here's going to be my theta axis, and here is my r axis. And what does the graph of r equals 1 plus sine of theta look like in r theta? So again, we're essentially treating this as kind of like this being our y, this being our x, and calling this graph y equals 1 plus sine of x. This is something you should know how to graph. We've dealt with much harder ones than this. So I've got a sine function, but it's being transformed. All that's changing is it's being shifted up 1. So I'm going to go up to a height of 2, and my sine function, instead of going through the origin and normally following a path that looks like this, so going up this way and then down and so on, it's going to start here and do the same thing. So I'm not allowed to cross that line up there. My graph looks like this. It goes up, down, up, down. And by the time we get to this point, where we've completed our one full period, we're at 2 pi. So there's 0. Here's pi, pi over 2, 3 pi over 2. And it goes similarly in this direction, but we don't even need to worry about the other parts. So there's the graph. There's the portion of the graph that I need, and I'm going to use that to now draw what the polar graph looks like on our Cartesian coordinates. So now I'm going to actually write these as the x and y axes, and I'm going to translate points from this graph to this graph. So the first things first, I want to figure out what is the length when theta is equal to 0. So when I'm pointing straight along the positive x-axis. Well, according to this, when theta is 0, r is 1. So I must be going through the point right here. There's a distance of 1. And what happens as we increase theta, so meaning I'm going to be going in this direction angle-wise, is our r is increasing. It's getting bigger and bigger and bigger up to a value of 2 when we're pointing in the direction of pi over 2. So pi over 2 is straight up and down. That must mean, in fact, let me adjust where I drew. Didn't leave myself enough room. Let's do it there. Let's say that's 1. So that means that that's 1, and that can be 2. So by the time I'm pointing, I started off here, by the time I'm pointing straight up, I'm at this point. So we've basically got, let me color code these, maybe this will make it easier. So here's the red point. It corresponds to this point right here. And then here's a blue point, and it corresponds to this point right here. And then green, I want to get this next point. Where is that going to correspond to? So that's when theta is equal to pi. R is back to 1 again. So theta equals pi, that's the negative x-axis, and we must be over here at negative 1 because we're pointing in this direction now. So 1, but in the direction of pi, which is out this way. So here's our green point. And then by the time we get all the way to 3 pi over 2, our radius is going to be 0. Out of colors here. Let me see if I can do, let's see what one of these other things does. I'll just see what this one does. So here's a crazy glitter color there. Here's the corresponding crazy glitter color there. So those 2 points are the same. And now we've just kind of got to figure out how to connect the dots. It's not just going to be a weird triangle. What we see happening is that R, so I'm going to focus on this section, connecting the red to the blue dot. R starts off at 1, but it's going up to 2, meaning as I go along this angle, what you can think of is kind of drawing in almost, there's the path that would follow if R stayed equal to 1 the whole time. Here's what the path would look like if it stayed equal to, boy, that is not very circular. Let me try to correct that a little bit, smooth that out. So here's the path if it stayed equal to 2 the whole time. But that's not what we're doing. We're going from R equals 1 up to R equals 2, from R equals 1 out to R equals 2, and it's increasing the whole time. So when I go in this direction, R needs to be a little bit bigger. And when I go in this direction, R needs to be a little bit bigger. And when I go in this direction, R needs to be a little bit bigger. And what we wind up getting is R smoothly going from a distance of 1. So I'm just increasing this length each time. And I smoothly transition from here up to here. And then to go back down, it's going to look exactly symmetric. So I'm going to go out through here and then back down to here. And then in this region, same thing. Our quadrant 3, as I go from this point to this point, I'm starting at a radius of 1, going down to 0, but doing it smoothly. You wind up getting a shape that's going to be from here down to here. And then lastly, from here back to where we started, it's going to be symmetric and smooth and follow that same shape. And we get this weird shape. This shape is called a cardioid because it kind of looks like a heart in this case. One big thing I want to point out between this example and the last. In this first example, I guess rather it was our third example, but in this example, R was equal to cosine of x. We normally associate cosine with the x coordinate, and notice our circle sticks out along the x-axis. In this case, we did a function that involved sine of theta, and we normally associate sine of theta with the y-axis, and sure enough, our cardioid here is sort of oriented along the y-axis. It sticks out. The furthest value it gets to is this 2, and it's along the y-axis. So just know that that's going to be true in general. If I just changed this thing to a cosine right here, I'd get the same shape, but instead of being oriented up this way, it would be oriented to the right this way along the positive x-axis. You'd get this whole thing basically just rotated 90 degrees down. So just keep that in mind. The difference between sine and cosine is just whether your shape is going to extend along the x-axis if you're dealing with cosines or along the y-axis if you're dealing with sines. So we've knocked out most of what we need. Let me talk about the symmetry, and then we'll go to some actually even more interesting shapes, and I'll finally actually go show you that table that my screen keeps snapping to accidentally. Okay. So one thing that can be useful, I'll just leave it like that, is talking about symmetry. There are different ways that these polar graphs can be symmetric. So let me just label them. Three different types of symmetry that we're going to look at. Something can be symmetric about the polar axis. Which is a really basically annoying way of saying the x-axis. So this is sometimes referred to here as the polar axis. Not terribly common. I would just refer to that as the x-axis, so I won't try to trip you up with that. If something's symmetric about the x-axis, basically what it's saying is if I were to replace the positive version of theta with the negative version of theta, I should be able to get the same result. So So this is mathematically how you can check whether or not this is going to be true. So in our case, this shape is not symmetric about the polar axis, meaning I want this to be basically the mirror. This top half is not a mirror image of the bottom half, so this does not have that symmetry. So let's go to one that does. Here, this one. This one has the symmetry that we're talking about. The positive half, the region above the axis, is supposed to look the same as the region below. So this should have that symmetry. Let me undo that. There we go. Let me go back to here. This is the equation that we're trying to deal with. So let's check that that's the case. R equals cosine theta. R equals cosine theta. So we've got, here it is with the positive version of theta, and here it is with the negative version of theta. R equals cosine of negative theta. But cosine is an even function, so that's the same thing as cosine of positive theta. And sure enough, we get the same thing in both cases, whether we use the positive version of theta or the negative version of theta. And this gives us that symmetry that we're talking about. That can help us draw. If we plug in, do this type of algebra to check to see what type of symmetry we're going to get, it'll limit the amount of drawing that we have to do. If I know that the top half is going to look the same as the bottom half, I only have to draw half the graph if I can verify that this is true. Similarly, we're going to have symmetric about, something can be symmetric about the y-axis. So symmetric about essentially theta equals pi over 2, which is our y-axis. And it turns out the check in this case to see if something is symmetric about the y-axis is we can replace theta with pi minus theta and see if we get the same result. There we go. So here's an example of one where that's true. I'm not going to go through the algebraic procedure like I did right here, but for this one, if you pick an angle of, for example, pi over 6-ish, which is ballpark it looks like this is at, and you did pi minus pi over 6, that would give you this same point right here. And the radius right here matches the radius right here. So these 2 points, we draw it in, this point is a mirror image of this point. Here's some value theta, here's the angle pi minus that same amount of theta. So there's our theta, here's that pi minus theta. So that's the example of what you would check to see if something is symmetric about the y-axis. And lastly, we can check to see whether something is symmetric about the pole, which is a fancy way of saying, oh, come on, about the pole, which is just a fancy way of saying the origin. So this is going to be like rotational symmetry. So in this case, what we can do is either replace, this is I think the easier one, r with negative r, or replace basically theta with theta plus pi and get the same thing. So maybe I should put my or here instead. So what this one's saying is, again, if I go back to our actual first example, way at the beginning, the circle. Here we go. For a given theta, here's a given theta, here's r. If I replace it with negative r, am I still on the graph? So basically, if I replace it with -8 going this direction, well, -8 means I would go this direction, and I'd be at that point, which is also on the graph. Alternatively, I could say here is r equals 8 when theta is roughly ballpark pi over 4 here. If I added pi to that, I'd be at 5 pi over 4, which is right here. And again, I'd have a radius of 8 at 5 pi over 4, and I'd be on the graph. So that's what that last one means. This one is symmetric about the origin. You can rotate this thing 180 degrees, and it'll look exactly the same. Okay. So we'll do some more examples, but I think the best thing to do is, let me just show you that table real quickly. Now I'm not going to be able to find it. Okay, here it is. Here's our table. And it shows everything that you need. So this table is in the book, table 7.3. I don't remember what page it's on, but I found it pretty easily. You can just scroll through the ebook to find this. It shows what polar equations give you lines. So here were the ones that we did before. Theta equals 0 gives you the x-axis. Theta equals pi over 2 gives you the y-axis. Theta equals just some constant gives you a line like the one we had earlier. And then you get weird equations for theta equal to these lines that that are parallel to one of the two coordinate axes but shifted off of it. So we're not going to encounter those a ton. Here is circles. So here's the circle centered at the origin, r equals a constant. Here is the circle r equals some number times cosine of theta. A cosine of theta gives you a circle oriented along the x-axis but off-center. R equals something times sine of theta gives you one oriented along the y-axis. And you can do, if r is equal to some constant times theta, it turns out it'll give you this spiral because the r value will just continue to grow as theta rotates. Some of these other shapes that we looked at earlier, let me zoom in here. I think we're at the maximum resolution of this thing. You can go check in the book. I think this is probably a little bit higher resolution. Here's one of the cardioids that we did earlier. Cardioids occur when basically this number that we're adding is the same as the coefficient of the cosine, basically. So it's saying you get these general thing called limicons. All of these shapes are called limicons. Whenever you do a constant plus or minus b cosine of theta or b sine of theta, a and b are constants here. If, in this case, this constant, the one that multiplies the trig function, is bigger than the other constant, so if b is larger than a, that's what it's saying here, if b is larger than a, you wind up getting the shape, but it has a little inner loop on the inside. We can see that in a minute. If the a and b turn out to be equal, you get one of the cardioids, so a equals b, you get a cardioid like we drew in our example earlier. And then these other ones, it kind of doesn't matter. You don't need to worry about these too much, the difference between these two at least. But if, excuse me, if a is larger than b, so if a is larger than b, forget about this part, you'll get one where it's just kind of a circle that's kind of squished in and dimpled on one side or flattened on one side. And lastly, we have these other ones. I'm not going to worry about them. Let's focus on these. You get these cool flower shapes. These occur whenever you start changing the factor that's being multiplied by theta within our function. So if I just have a cosine of n theta and I make n be a number that isn't just 1, so it's not just cosine of theta, but cosine of or sine of 2 theta or 4 theta or 3 theta or 5 theta, you start getting these petals. And it turns out if this number is an even number, you'll get twice as many petals whenever it's even. But if it's odd, you turn out to get just the exact same number of petals. So here it's 3 and we get 3 petals. Here it's 5, we get 5 petals. But in the two even cases, when it was 2, we got 4 petals. When it was 4, we got 8 petals. So let me give you just a quick sense of why these graphs look the way they do and show you how we can use Desmos. Let me see if I can bring that up here on the screen. Okay, there's that. Don't want that. Okay, so let me move this over so it's all in the screen here. Kind of zoom this out a little bit. Okay. So I've got this set up. You do not need to do anything this fancy. This is the equation over here that we're going to be graphing. 3 times the sine of 2 theta. So this should give us one of those roses, and because it's even, it's a factor of 2 here, we should get double that many petals. So we should wind up with 4 petals in this case. All I've done is basically set this up to draw a bunch of stuff, and here is sort of where I'm going to change theta. So right now I'm saying I'm going to go along this direction. So this orange dotted line gives us the direction that theta is currently pointed in. This blue dot gives us basically an actual coordinate, the r theta coordinate or xy coordinate. And I'm graphing at theta equals 0. So in this direction, theta is equal to 0. I plug in theta equals 0. 2 times 0 is still 0. The sine of 0 is 0. And therefore, our radius that this is going to spit out is going to be 0. And that's why our radius is right here at the origin. We haven't gone any distance. And that corresponds to this picture. So this green graph right down here is this graph. It has an amplitude of 3, as we can see, right? 1, 2, 3. And it's oscillating twice as quickly. So it's a sine function that oscillates twice as quickly as it normally would. And so by the time we get here, here's our 2 pi. It's done 2 full oscillations. So all I want to do is start moving the value of theta. So I'm going to start increasing it just a little bit and see what happens. So notice as I start to increase theta, let's stop it here. As I've increased theta a little bit, we've just moved up on our graph down here, right? As I increase theta, this graph, we're just tracking along this graph, the y value's increasing. And what we're similarly doing is just, so again, this is meant to indicate the height of this graph is the radius of this graph. So as I move to the right and increase theta, the radius has increased up to, looks like a little bit over 1.5 almost. And that's what we've done here. We've increased our radius. We're again going in this direction. Here's our theta direction now. We've increased it beyond 0. And our distance that we're going is now out past, a little past 1. This is a distance of 2 right here. This would be a distance of 1 right here. And so this is a little bit more. And as we continue to increase theta, we eventually get to the point that we max out our radius. We're at a distance right now of 3. We are a distance of 3 away from the origin. We are at the point where sine is equal to, in fact, not quite. Yeah, so we basically maximized out our radius of 3 here. I guess it does look like we're pretty close to that maximum point. Where basically we've gotten to the point where theta is equal to pi over 4. So coming to this part, theta is pi over 4. We double pi over 4 and you get pi over 2. The sine of pi over 2, that's straight up. The sine, when you're pointing straight up on the unit circle, is 1. 3 times that 1 gives us our radius of 3. And as we continue, it draws out, here's the parts where now the radius is down in the negative. So we're aimed into the second quadrant, but because our radius is negative, we're actually drawing back here in the fourth quadrant. And we continue on like this around until we complete the entire shape. So this is the idea of how we can do some of these things. Again, this is more complicated than what you need to do, but it's kind of fun to play with. I borrowed this from somebody that's really good with Desmos, and they showed me how to set this up. But for us, if I just wanted to do something a little bit easier, Let me see if I can just get things reoriented here. Sorry. Let me just hide all of these for now. I want to hide all of these parts down in here. I don't need to see that mini graph. Oh, it's going to be easier to just open a new tab. Let's open a new tab. So desmos.com. So if I just wanted to know what R equals, so we can do it as simply as this. In Desmos, if you just use the letter R and the word theta, it'll convert that theta to the angle, you can do these graphs. If I want R equals 1 plus 2 times the sine of parentheses, I'm going to write out the word theta, and it converts it to the angle. Boom, there's our picture. It draws it for us. So if you want to check your work on any of these problems, Desmos will do these graphs for you. If I want to instead do R equals, I don't know, 2 times the cosine of 3 theta. There's our 3-petaled rose or flower. So it'll do all of these ones for us. You can check your work. Let's do 2 times the sine of 6 theta. Now we've got a 12-petaled graph because the number we plugged in here is an even number, so we get double that number of petals. So Desmos is a really powerful tool. It's a really good way to check your work as you do some of these problems. I'd highly encourage you to use it. And otherwise, I think that's hopefully good enough for now. Give this a shot, see how it goes, and let me know if you have any questions.